Everyone, today we're going to be focusing on the discriminant in a quadratic equation, so b squared minus 4ac. And what I love about the discriminant when it comes to quadratics is how much this actually tells us about the quadratic itself. Now, the discriminant tells us two really big things, and that is the nature of solutions in a quadratic equation, as well as the number of solutions to a quadratic. So, when we calculate our discriminant, if our discriminant is equal to 0, then that means we have one solution and that the nature of that solution is a rational solution. So what that means is that it can just be written as a fraction p over q, and that's because our discriminant just ends up being that b squared. Our solution ends up being that opposite b over 2a, right? Because we get rid of that whole square root part in our fraction. So we end up with one rational solution. Now, if our discriminant is greater than 0, we know that this means we have two solutions, okay? If our discriminant is a perfect square, so if that's something like 1, 4, 9, 16, so on, that means that we have two rational solutions. And once again, that's because that square root simplifies to a whole number, and then we can simplify that numerator in the fraction. On the converse, if let's say we have a discriminant that is above 0, but it's not a perfect square, so something like 3, 7, 21, etc., then you've got two irrational solutions. Okay, and that's because we end up with that really ugly, like -3 plus or minus the square root of 19 over 4. And so we end up with two irrational solutions. Then we know that if we've got a discriminant less than 0, that we have 0 solutions. But what we mean by 0 solutions is we have no real solutions. Okay, and that's because especially in methods, we can't square root a negative number. So we end up with no real solutions, but if we looked at imaginary numbers, then you would have some solutions in there, okay? So when it comes to calculating the discriminant, you want to identify your A, your B, and your C, because our discriminant is equal to b squared minus 4 times A times C. So in this case, our discriminant is going to be -8 squared minus 4 times 2 times 5, okay? -8 squared is 64, and then we're going to take away 40, and that is 24. Now, 24 is not a perfect square, so we have two irrational solutions for this one. Okay, so we still have two solutions. We've got two x-intercepts, but they're going to be irrational. Now for this one here, you're first going to have to move everything over to one side, because when we solve the discriminant, that's always when the function is equal to 0. So I've got 6x squared take 4x plus 1 is equal to 0, with 6 being my A, -4 being my B, and C being 1. Then we're going to do the same thing. We're going to find our discriminant. We've got -4 squared minus 4 times 6 times 1. So I've got 16 take away 24, which is -8. So I have no real solutions for that one, okay? That just very quickly tells you if your graph is crossing the x-axis, how many times it does, if you're above, below, so on, okay? Now, when it comes to using the discriminant for more tricky problems, right, we talked about solving quadratic inequalities earlier, and that's what you do when it comes to the discriminant, is you're solving a quadratic inequality. So first you need to consider your discriminant to be its own function, right? It's going to end up being its own ax squared plus bx plus c. Then you're going to sketch the graph of the discriminant against whatever parameter you have. So we might have things like m or p thrown in there, and then you find that region that matches your solution. So we'll look at an example of this. So the quadratic equation we're working with is this one here, and something really important to note, I didn't the first time round, is that this is a positive integer. So you're going to find that for a lot of these questions, you have two solutions, but you can only count one because we're only looking for positive integers. Now, in this case, I've still got A, B, and C in here. So my discriminant, being b squared minus 4ac, is going to be 10 squared take away 4 times A again. So my discriminant is equal to 100 minus 4a squared. What we're going to do with this information is sketch our discriminant function, but instead of x and y, we've got a and the discriminant. And for 100 minus 4a squared, I know that my turning point and intercept are going to be at 0, 100, and that my two intercepts here are going to be at -5 and 5. Now, because you're just doing some quick working out, you don't need to write the coordinates down for this one. You're just doing a quick sketch. Now, what we want to know is for which values we have one solution. For the values that have one solution, we're going to be looking for where our x-intercepts occur. So remember from our solving quadratic inequalities, that being equal to 0 was that one solution, that x-intercept. So in this case, the only solutions that I possibly have are a equals -5 and a equals 5. Okay, now we could have solved the inequality as per normal with that one. But looking at our graph, these are the two solutions we've got. We do have to discount a equals -5 because we want positive integers only. Okay, so that's just something to keep an eye out for with a question like this one. Now for part B, we're looking at what values of a does the function have two solutions. Now it doesn't say two irrational or rational, it just says two solutions. Once again, something to keep in mind is that we can have no negatives and no 0 because we're looking for positive integers. The other reason we can't have 0 is because if I sub in a equals 0 to the above, I don't have a quadratic anymore. Okay, so no 0 and no negatives for this particular question. From our graph, we can see that we are above the x-axis between -5 and 5, right? So currently, I know that a can be bigger than -5 and bigger than 5, but we have to discount this left-hand side, and that's due to the positive integers only. So the actual answer for this one would be for a less than 5 but greater than 0. Okay, that's why we've got two solutions for this one. Now for two rational solutions, this is one where you do just have to plug things in, and there's not a lot of room here to do that. So just pick a few to work with. But two rational solutions just means that we've got a perfect square. Okay, so there's going to be some values of a for which we have a perfect square happen. Now, perfect squares, once again, are things like 1, 4, 9, 16, so on. So just pick two of those to work with. I'm going to work with 4 and 16 in this case. So if we had 4 equals 100 minus 4a squared, we're just going to solve that as per usual. So taking away 100 and dividing by -4, I've got -96 over 4 is equal to a squared. I can simplify that down. I've got -24 over 1 equals a squared. So that should be positive, my bad, positive 96 and positive 24. So a is equal to the positive or negative square root of 24. Now remember, we can't have that negative due to a being a positive integer. So a is going to be equal to the positive square root of 24, and we can pull out a square of 4 from there, so we end up with 2 square root of 12. Not square root of 12, square root of 6. So 2 root 6 is our one of our a values, which would give us a rational solution. Let's try this same thing with, I'll do 36 instead of 16, is equal to 100 minus 4a squared. So I'm going to end up with a squared is equal to 64 over 4. That's 16, so I have a is the positive or negative square root of 16. Once again, we cannot have that negative, so a is going to be equal to positive 4. Okay, so they're just two of the values of a, which would give me two rational solutions. Okay, so that's one application of our discriminant. Now, if we want values of a for which we have no solutions, that's looking at what point our discriminant function went below the the a axis in this point. And in this point, that happened between -5 and 5. Once again, we can't have Sorry, I've drawn that upside down. Once again, we can't have that negative side. So it's only this point onwards which we can count. So A has to be greater than 5 in this case for it to have no solutions. Okay. Now, feel free to give this next one a go by yourself if you would like, but we're going to apply the same sort of concept. If we've got no real solutions for this function here, that means we're going to graph it and see where we are below the p-axis in this case. Calculating my discriminant, I end up with negative 2p squared minus 4 times p times 1. That's going to give me 4p squared minus 4p. And I can take out a common factor of 4p just to help graph that out. So if I was to graph this, I can now see that my two intercepts happen at p equals 1 and p equals 0. I have once again drawn that upside down, as you do, but p equals 1 and p equals 0 are my 2 points, my two intercepts. And if I want no real solutions, I'm going to be looking at the part of that graph that is below the the p-axis in this point. And in this case, we're working with values between 0 and 1. So for us to have no real solutions, p has to be greater than 0, but less than 1.